So second session will also be handled by an industry expert. He is Dr. Arun Shaji. Is an accomplished Arun Shaji will be handling the session. So a brief introduction about the expert. Dr. Arun Shaji is an accomplished researcher and educator with over 13 years of experience in RF, microwave and embedded system, spanning research, development and teaching. He holds a PhD in Electronics and Communication Engineering from Cochin University of Science and Technology, CUSAT, where his research focused on metamaterial-based antenna design and microwave application. Dr. Arun's research expertise includes the design and analysis of metamaterials and metasurfaces for antenna gain enhancement, switchable and tunable metamaterial structures, and wideband and compact antenna system for advanced applications such as ground penetration radar, passive synthetic aperture radar. He has extensive experience with leading electromagnetic simulation tools such as HFSS, CST Studio, ADS, as well as programming proficiency in MATLAB, Python, C++ for data analysis and processing. Currently, Dr. Arun is associated with Auxins Lab Private Limited, Trivandrum, a startup focusing on innovative solutions in satellite communication, radar systems, and RF front-end design. His work includes RF amplifier development, SDR interfacing, and hardware prototyping using platforms like Raspberry Pi and Arduino. He has published multiple research papers in reputed international journals and conferences. He is also a qualified UGC NET multiple times, and he is a member of professional bodies such as IEEE, IUT, and IUT. Good evening, Professor.
Yeah, good evening, ma'am. That was a nice
Okay.
introduction from your side. So thank you very
You.
much for the introduction, and good evening, every participant. So myself, Dr. Arun, presently working with Auxins Lab Private Limited. We are based out of Trivandrum. We are in the design of different RF content system design, as well as the antennas and the various filters, amplifier design, and so on. So in this presentation, I would like to take you through the kind of works that we do in our company, plus the research works which I have done, that I will be sharing. So since I have also done in metamaterial, all the speakers are touching mostly on metamaterial, those kind of stuff. So I will also go through the metamaterial stuff and the parameter extraction, like the permittivity, permeability, and those kind of stuff as well. So I will share my presentation now. So first I will go to the introduction about my company. So our company is Auxins Lab, where we have a target like a sensing the unseen. So I am presently serving as the secretary of MTTS Kerala section, also a research engineer at Auxins Lab Trivandrum. So in our company, what we are working on is about different target lines. So first product is called the weather forecasting. Second one is ground penetrating radar. Third one, passive synthetic aperture radar, RF intelligence, and electronic intelligence. So these are the different areas in which we are working out. So some of which we have products as, and some of which we are on the research phase. So first one is called the Enhancement. So this is sensing the atmosphere. So we are concentrated on hyperlocal weather prediction on concentrated areas of 5 kilometer radius. So you may be aware of different kinds of weather forecasting modalities available. So for example, for weather forecasting, it requires a lot of sensor data. So sometimes, even though there are a lot of sensor data, the prediction fails during extreme weather events. For example, nowadays we are experiencing sudden thunder storms, which is concentrated on a particular area where the rain intensity level is very higher, thereby causing floods. So these kind of weathers, if we can predict earlier, then we can be able to save extreme weather events like landslides and so on. So accuracy of weather predictions depends upon how well we model the atmosphere and the availability of atmospheric measurement methods. So moreover, all the kind of prediction methods works based upon some models. So the input that we are giving into the model is the key requirement of giving the better prediction. So how the input can be increased, that is what we are working on the hyperlocal prediction modality. So the existing sensing methods are space-borne radio occultation, where we have where the radars will be placed on aircrafts and high altitude vehicles. Thereby, the satellite signals would be taken, and by means of which the weather will be sent. Second thing is the airborne, which is radio sonde balloon. This is normally the Indian meteorology department people used to do. They launch weather balloons, so they'll which carry the sensor modalities. So third is by means of radars. So there are different kinds of research radars are also available. We had one at Cochin University of Science and Technology, where this radar is used for vertical profiling to find out the wind turbulences as well as the different kind of predictions. So the excessive problem is the lack of data. So the launching of weather balloons as well as taking out the sensor data at all the locations is not possible. Also, the frequency of this radio sensor balloon is also not that intensive. So we are coming up with a solution in which we are taking the refractive profile at high resolution. So this how we can extract the refractive profile of the atmosphere. So we present Ensonde, which leveraging GNSS signal sensing for high resolution refractive profile enabling hyperlocal weather forecasting. So here what the idea is that we all know about the GNSS satellite. So we have many GPS satellites. So GPS satellites, Beidou and GLONASS, those different kinds of satellites are there. All the satellites are emitting signals from there by which the location information we are getting. So those signals are passively taken by our receivers. So using that signals, we'll find out the delay that is caused due to the atmospheric parameters. So those delays are taken into account, and by which our algorithm works for extracting the refractive index of the profile by which the weather predictions can be made. So this sensor atmospheric sounding system has observation. We have multiple receivers placed at different locations, and observation processing module and N-Recon is an algorithm that is working on that. So the output of the algorithm is fed to numerical weather prediction models by which prediction in the range of hourly, 2 hours, 3 hours predictions can be made. So normally this is the sensors are or the receivers are placed in a cells in which we take a cell to be of 5 kilometer by 5 kilometer resolution, in which we kept different sensors at a minimum of 4 sensors. So thereby the entire vertical profiling of that particular region can be obtained. So presently we are keeping these sensors at different locations at Trivandrum. So this yeah this system we are also working with Kerala Disaster Management, and we are piloting it at Kannur district in Kerala, where there is a large amount of landslides happening in those areas, Kannur, Wayanad, and so on. So our company, in collaboration with IIT Roorkee, providing this solution of predicting the landslide. So there are different applications like precipitation prediction, cloud coverage, clear air turbulence, and so on by use of this in sorting. So we have some patents on that and some papers also published regarding it. So this is about the immediate deployments that we are planning. So this is a different kind of data acquisition procedures that we are doing. So this is the end-sounded monitor dashboard that we have. so in which the pressure, temperature, and humidity are collected on daily basis, and that is fed to the model. So the second product is called as Live, which is called as Locate, Image, Find, and Evacuate. So this is called the otherwise we call it as ground penetrating radar. So this ground penetrating radar is used to map the subsurface. So this application is on different scenarios. One is on the water authority. We are working together with Kerala Water Authority in finding out the underground piping so that they can clearly map where it is and how it is made and so on. And we are also researching on finding out the leakage in pipes. Also, we are working with a client who want to know the depth of ice bed. For example, if you see foreign countries, snowfalls are there. So there are some agencies who remove the snowfall. So they remove the snows based upon, or they will make a budget calculation based upon the thickness of the snow that is on the road and so on. So this instrument or this DPR will help us to find out how much depth the snowfall is and so on. So this ground penetrating radar that uses RF pulses to image the surface. Here we are using the technology switch frequency continuous wave radar. So the problem is for a subsurface mapping that addresses the challenges of underground material detection and 3D reconstruction. So the thing is that it needs deep penetration with high precision and accuracy. So since we are using the switch frequency continuous wave method, where we are using low power radars, so the penetration would be less. So how we can improve that, and how the accuracy and precision in terms of depth and the size of the target and so on can be done, that is what we are working on. So for this we require a small form factor kind of product by which we can base it on a drone based deployment. So the challenging thing is that we need a wideband antenna, so which is having a small form factor, that is small size, that is compact. So if you see, the working frequency is in the lower order frequency range. As you know that normally the size of the antenna is of the order of lambda by 4. So if you see about a very low frequency below 1000 megahertz and down, if you think of an wideband antenna which is of low size, that is a challenging thing, that is not there in the literature also. So if you go through the literature, it will be available, but mostly we used to attain the wide bandwidth, but we don't have the directionality in the antenna. We'll be able to attain the wide bandwidth, but when we check the directionality, it will not be the same for all the frequencies. So the thing is that we have horn antennas of the range, but it is of very high size, and other kind of antennas like bow tie antenna, Vivaldi antennas are also there. So increase the depth, reconstruction of subsurface objects, these are our requirements. So these are some of the benefits of SFCW radar, which is having high resolution, high sensitivity, wide dynamic range, frequency agility, low sampling rate, low power consumption. So we can deploy for large amount of time in some places. So that is the use case. So the solution is modeled like this. The like one is the data acquisition part, and another one is the post processing part. So the data acquisition part is the hardware modules and so on, and the post processing part, we will take the data and then we'll post process, or we can process on the site itself. So both the way we can do, but the kind of 3D reconstruction, those kind of things are done in the post processing. So this is system architecture. We have transmitting receiving antenna. We have control unit, GPS module to know the path of the system in which we are making the measurement. Processing unit, we will find out the radargram. So radargram is the immediate result. That is a 2D kind of thing that is getting from the GPR. So then from that radargram, we have to reconstruct to get the 3D shapes and so on. So the frequency level which we're working is 100 megahertz to 600 megahertz, power level 10 dBm, power which is 0.1 milliwatt, step size is 10 megahertz, number of points 50, and depth tested is 1 meter. So presently we are planning up to 6 meters. So this is a Bowtie antenna design. This is a high heavy size, which is 2 feet by 1 feet size, which is initially tested, and we are this is a old photo in which we are working on that frequency range. So this is the kind of radargram which we are getting. So from this is the as I told you, this is the radagram. So this hyperbolas which is shown with the arrow marks is shows some kind of target. So using this radagram, everyone cannot be able to understand what is the kind of target and how the shape and so on. So that 3D reconstruction is necessary, and that has to be accomplished. So these are the different kinds of radagrams obtained. So the post processing has these parts. So the we will call the different kind of scanning mechanism. Suppose if you send a pulse and then it comes back at a particular point, then we call it as A scan. And if you take that and move to some area, so for example, if you move towards y-axis and if you take a series of A scan, that is called B scan, and when you do it on the other direction also, then it is becomes C scan. So C scan is necessary in order to reconstruct the 3D image. So different methods are used for that. So the we our objective or our product line is working on basic life prototype, increased depth up to 330 meters, 3D reconstruction algorithm, 3 GPA prototype using quantum sensors, urban utility mapping, detection of soil properties, detection of human presence, detection of mines, chemicals, etc. So the next product is passive synthetic aperture radar. So you might have heard about a synthetic aperture radar that is used for mapping the enemy military areas and so on, because you all know that the hyperspectral imaging cannot be done during kind of extreme weather conditions. Like if it is very cloudy, it will be very difficult to find out the hyperspectral imaging. So in that conditions, what we can do is we can go for this passive the synthetic aperture radar. So this passive synthetic aperture radar, in the sense we are not using the active radar. So we are taking the signals from the other radar signals from the atmosphere, that is impinging the target, which is the earth surface, and coming back we will take that and we will analyze it. So the acquisition of direct and indirect signals from GPS and Ku band satellites. Now you may be aware of the Starlink satellites that is present everywhere. So that one also you can use. That is also working in some 8 to 12 gigahertz or something like that. That one also you'll be able to use. So processing of the signals for target detection, extraction of 3D tomography. So this is a kind of data acquisition which we have done using two helical antennas, one uh, facing the space and another one facing the ground. So these are some of the star images. This is not our images. This is just for your sake of understanding. So next one is RF intelligence. The next product. This process involves the detection and the identification of RF sources in a particular region of interest. So this one we are working with defense Indian defense system. So this electronic intelligence. So I'm not speaking much on this one. RF intelligence and electronic intelligence. So that these are the different product lines we are working on in our company. So yeah. So that's all about my company. We are looking for bright persons to join in our company. So we are based out of Toronto. So if someone is some of your students are very much interested and they are well knowledgeable and so on, you can ask them to visit our company website and apply on. So that's it about an introduction about a company. Now I'll go on to the uh, research topic. So if you have some questions on this area, you can ask me. Then I will go on to the research.
Participants, if you have any queries, you can ask.
Sir, what are the requirements needed to get the job in this company, sir, for student? Which area? Only the about the radar or any other thing, sir?
So we are in this RF front end design as well as the entire system design. So we are actually looking for some person who is very much interested and who knows something, like not very much pressure, but uh, who can do something in RF related, or they can embedded or signal processing. These are the three areas which we are looking. Okay.
Okay, sir. Corresponding tools, sir.
Corresponding tool, if you see, presently we are requiring some
Everyone or
signal. Yeah, yeah.
everyone is expected for skill based, no, sir. That's why I'm asking.
Yeah, for example, we are looking for signal processing. So signal processing engineers should understand the kind of signal, like what is chip signal, what is impulse signal, and those kind of concepts. And they should be good in programming also, like Python scripting as well as the MATLAB kind of thing. If you look about RF and those kind of stuff, uh, they should know this RF PCB design. That is one thing. And why I'm not insisting on HFSS and those kind of things. Those things plus the PCB design will add a good advantage, because everyone knows HFSS to a small extent, not too much, but yeah. Otherwise, the HFSS together with the ADS, if you want to design some amplifier and so on, uh, we need ADS till the layout level, not only the design. After the design, you have to make it as a layout also, like the footprint and so on. Yeah.
Thank you, sir.
Yes. I think I will go on to the next presentation. So this is about metamaterial superstrates for gain enhancement in packed antennas. So, so here I am going to, so everyone speaking about metamaterial. So I will just touch upon some of the areas in which I have worked and I have seen in different industries also. So for example, so one second before that, I'll just share one thing. So as I am the secretary of MTTS Kerala section, so I will just tell you about the conference that is going on in this Kerala, Cochin. I think most of you may be aware of about that. It's MapCon 2025. So this is happening in Cochin. You can all be a part of that. So there are many kind of initiatives there. So I think most of the initiatives have finished, like BTech initiative, MTech initiative, uh, PhD initiative, and so on. Everything was there. So, but still you can attend in different kind of workshops, like partly. I think they have given a very small registration fees of 100 rupees, 500 rupees, and so on. So it is easy for you to attend. The attractive thing of this is that it is an international workshop where multiple delegates from various countries are participating. Yeah, that's it. So we move on to the presentation. So here I am going to speak about the introduction, superstrates for gain enhancement, iterative G-shaped metamaterial superstrate, active metamaterial superstrate, interdigital capacitance electric ring resonators, low loss metamaterial superstrates, and conclusion, references, and appendix. In appendix there are two different kinds of extraction methods used for extracting the permittivity and permeability value of the metamaterial is used. One is the Nicholson-Rossiter method, and another one is the generalized sheet transition condition method. So these are the two methods which is verified and compared. So as you all know about the antennas, there are different kinds of antennas available: wire antennas, aperture antennas, and so on. Everywhere the radiation pattern plays a major important role. So when you go to industry and so on, where radiation pattern is very much important. For example, when we do some research and so on, we does not care more about the radiation pattern, whereas we'll just put some cross and something, and we will just keep it like that. But in the industry perspective, they will look on into each radiation pattern very clearly, and they will ask how much it can reduce and so on, or how much it is directional, how much is the isolation, and so on. So here I have concentrated on working on the gain enhancement. So this is the normal kind of thing which is I have worked earlier. So we have used different kinds of superstrates for enhancing the gain enhancement. So suppose if I am working on this GPR also, as I told you earlier, where we are looking on only the directional antennas, not the other kind of antennas, because directional antennas are very much required. Then only the efficiency of the antenna will be more. So suppose we are using a power level of 10 dBm at the transmitter. If 8 dBm goes away because of the transmission losses, then that doesn't make any sense. So efficiency is very important. So the gain formulas and all, you know. So the gain comparison, the gain measurement method which we use is the normal two antenna method, which is called as gain comparison method, where we will keep this one antenna, two horn antennas, standard horn antennas, and then we'll replace the horn antennas, and we will keep the material. So for the gain comparison, so the gain measurement, it is not necessary that you require an anechoic chamber or something. You can use the normal place itself without any kind of reflectors. It will give you a very correct value for gain, not for the radiation pattern. So the need for gain enhancement is increase the signal strength, extended range, improved signal quality, directivity, compensation for losses, efficient use of power. So metamaterials, as you all know, that it is artificially engineered structures where we change the structural parameters, thereby we can change the property like permittivity, permeability, and refractive indexes based on our requirement. So what about a requirement we will use? For example, metamaterials nowadays, it is used for gain enhancement. It is used for shielding applications. It is used for clocking application. It is used for antenna arrays and many reconfigurable structures, reflectors, and many things. So these are the people who are behind this. So you all know about the different kind of materials based upon this quadrant, which is the normal dielectric materials and epsilon negative materials, mu negative, and the left-handed materials, or the negative refractive index material. So the parameter extraction method that is used throughout the research is modified Nicholson-Roswell method and GSTC method. That is the different method. So generalized sheet transition condition method, where we are taking the ABCD parameters from the S parameters, and thereby finding out the epsilon and mu value. So superstrates. So there are different arrangements of superstrates that is used. One is horizontal arrangements, vertical arrangements, and so on. So when people are doing research on this metamaterial, they sometimes don't know, not everyone, perhaps some people may be there, they have not seen metamaterial used by any people. So sometimes some of you may be there in this participant. So you may be hearing about this metamaterial and so on. So where it is used, you may have a doubt. So I too have not seen the material as such used in any industry. But last year when I went to MapCon, which happened in Hyderabad, there I was surprised to see many of our Indian defense systems. They are using in their missiles. In the missile, you know about the cockpit, the front cone-shaped area. In the front cone-shaped area, fully it is covered by this metamaterial structures. So even though we gone through the research papers where we will say that metamaterial it is used for absorption, like this absorbers selectively can send the signals inside, all other frequencies will be reflected out and so on, but it is used. Similarly, you might have heard about Astra Microwave. Astra Microwave is a Hyderabad, Bangalore based company. They are also working for different. They have come with an antenna array which is made up of this metamaterial structure. So there are many applications that is going on, and people are working on this 5G 6G kind of reflect array that is also available in the market in a smaller scale. So in this research, I have used a normal rectangular patch antenna in which a superstrate is used for enhancing the gain. So this is a normal microstrip patch antenna that is working at 2.4 gigahertz. Yeah,
Excuse me, sir.
yeah.
So what kind of material to be used for super electric material or same material or some other material, sir?
Can you repeat once again?
What is the material to be used for a superstate, sir, to the superstate?
What is the material used for the superstrate, right?
Sir.
Yeah. So your question is what is the material used for superstrate, right?
Yes, sir.
So the material used is here in this papers, all the papers which I have used is the FR4 substrate, as well as another one substrate that is custom made for getting a high permittivity value. So you
Okay.
can use, yeah.
It means if you have more structures, then it is called a superstate with the dielectric material.
No, no. You are asking the meaning of the superstate is just uh, like if in the above the antenna we are keeping this metamaterial. That is why it is called superstate. Substrate, superstate above the antenna. That's it. So it is just kept above the antenna. So it can be kept as layers or it can be kept as a single layer and so on. Okay. It's
Okay,
just a
sir.
terminology that is used. Okay.
Okay,
So
sir.
it is nothing else. Yeah. So the benefits of superstates are gain enhancement. We can beam steering, improved front to back ratio, bandwidth enhancements. So the need for gain enhancement using superstates, so limited space and size constraints, so frequency bands, spectrum efficiency, radiation pattern control, mitigating multipath interference, beam steering, and so on. So mounting on superstates can be done in different ways. So it can be single layered or multiple layered mounting on superstates. Again, enhancement has to be done carefully in order that the radiation property of the antenna is not altered. Yes. So the approaches used for gain enhancement is two things. One is the fabric around cavity. So FP cavity means we are keeping a uh, patch antenna above which we are keeping a superstate. So it is forming a cavity, therefore multiple reflections happens. That's why it is called like that near zero refractive index property. So that I will explain again. So this is the FP cavity. So we have the antenna here, and we have a superstate over here, and multiple reflections. So when it is coming in alignment, it helps in increasing the power level, thereby increasing the gain of the antenna. So multiple reflections, and the superstate is also having a near zero effect also. So near zero effect means it will converge the beams towards the normal, and thereby the gain enhancement is formed. So the fabric parrot cavity, so whatever structures where the fabric parrot cavity is attained, where we are using this formula to find out the height between the antenna and the superstate. So in this formula, we are substituting the reflection phase of the ground plane and the reflection phase of the superstate. So near zero material. So according to Snell's law, when electromagnetic waves propagate from near zero refractive index to free space, the wave directed towards the normal, because it is moving from a low refractive index to high refractive index. So it will be directed towards the normal. So the types of superstates used here is dielectric superstates, yeah, reconfigurable low loss. So these are different terminologies used. no need of confusing. Like people call it as FSS, frequency selective surface, metamaterial, and many other names, right? So these names are used, catchy names are used for uniqueness in their design and so on. Otherwise, most of them are having some resonant properties. That's why, yeah. So the methodology used is first we design the unit cell and simulation and verification of the designs using HFSS, then extraction of the parameters using some algorithm, maybe Python based or MATLAB based. Presently, it can be done in the CSC software. CSC software, the extraction of epsilon and mu is available as such. HFSS, I have not seen that one, maybe available in the latest version of that. Application of the prototype, measurement of antenna parameters using vector intercalation. So first shape is this iterative G shape. So I will just tell you about the importance of each thing and will go on very faster. So this the idea is based on reducing the size using the fractal concept in mind. So fractal concept is also an idea of increasing the effective length of the resonance structure. So here also, as the number of iterations increases in the G structure, the resonance can be made to the lower frequency rates. As you see in this one, dark blue shows the resonance of the single G, and when we increase the number of G inside, what happens is the resonance comes inside. So that is the idea of using this structure. So thereby the size also was kept to minimum. So normally metamaterial cells are defined like this. It should be that it should have some properties in terms of permittivity and permeability, and also it should be very much less than lambda by 4. So these are the two conditions. So it should be very less, thereby resonating at the frequency of interest, and also some property like permeability, those negative values has to be attained. So nowadays there are different kind of structures available where people are working on shielding effect, where even though these properties are not there, if the length is less and if it can work for a different polarization, converters, and different kinds of things are also available. So this is the simulation setup which is used for parameter extraction. So what I have done is I have not used the flockade port for this. I have just used the wave port. You might have an idea about the wave port and flockade port uh, in HFSS. So I have used the wave port in HFSS to excite. So also the direction of excitation is similar to the direction in which it is kept over the antenna. So I used to keep the antenna. I used to keep this unit cell in a horizontal shape above the antenna. That is how I have done. So this top and bottom is taken as perfect magnetic layer, and the other two sides are taken perfect electric layer, and the two sides on the screen is used for the excitation. So refractive index is extracted using this modified Nicholson-Ross square method, and near zero refractive index is obtained at 2.4 gigahertz. So this
Sir,
is
excuse me,
the,
sir.
yeah.
So what is the use of that, sir? I think both PEC and PMC on the same material.
Yeah. So normally why we are keeping that is our idea is that the should metamaterial is also called as periodic structures, right? So periodic structure means it should be kept periodically. Also, it should have the same property. Okay. So if you keep this PEC and PMC on both the sides, what it acts like a mirror. So instead of keeping it as an array, a single unit cell itself, when you keep this PMC and PEC, it will have the same effect as that of an array. Do you understand? So
Yes.
the array as well as the single unit cell should behave similarly. That is the idea. Okay. So in CST or HFSS, I think you can keep the unit cell a single unit cell. Nowadays you can directly simulate this periodic structure. So when you take that periodic structure, you can keep the unit cell, and when you click another option, the entire array will be coming. If some of you have experience, you can see that. Yeah. So this is our unit cell, finalized unit cell, which is I think it is of the order of 22.5 by 22.5 mm. So we have stopped the iteration to third iteration because again increasing the iteration reduces the size of the G, and once it goes beyond behind the 0.mm, 1 mm and all, it is difficult to fabricate. So otherwise the effect is more or less the same. When you add again G, it does not change the properties of it. So this is an equivalent circuit that is made of this. As you all know that papers, they will ask for some equivalent circuits or something. So this equivalent circuit is designed using the material property only. So I have not gone for some equations and so on, such similarly as the filter people do. People who design filter, they will come up with some equations, and they will finally come up with the equations, and they will finalize the equivalence. So what I have done is based upon the electric field vector direction, I have seen how many inductors and capacitors are there. For example, if I take this electric field direction this vertically, I will see parallel E is going on this way, and when I see this way, I can find an inductor here. When I see the second one, I can see an inductor and a gap is there. I will consider it as a capacitor. Similarly, this circuit is constructed and it is simulated in ADS, and I have got it the simulated as well as the equivalent circuit S11, S21 to be the same. So this is the microstrip patch antenna that is used for throughout the all the structures which I have used. So this microstrip antenna, as you all know it. So this microstrip patch antenna is actually what I can say, normal rectangular microstrip patch antenna that is working at uh, 2.4 gigahertz. One second. Okay, this microstrip patch antenna is working as 2.4 gigahertz, which is having linear polarized. It is not circular. It is linear polarized. Uh, yeah. So this is how the antenna, this superstrate is kept over the antenna. You can see the patch antenna on the ground and the superstrate over the top. Superstrate acts as a partial reflective surface of the fabric cavity. So the ground plane has a reflection phase of 180 degree, and the reflection phase of the superstrate is minus 110 degree. So reflection phase is the S11 phase value. So when we are calculating using this formula as I told you earlier, and we got the distance to be 12 mm, and that is the height at which the superstate is kept, and the height gain enhancement is obtained. So these are the fabricated prototypes. So these are the electric field analysis which we have done, at which so different kind of analysis were done using this different orientations of this G. So here you can see the G is kept on one direction, another one is kept on different directions. So more or less the gain enhancement is the same. So the gain enhancement of about 4 dB is obtained here. So yeah, these are the different concentration of electric field at different heights. So at 5 mm above the antenna, 12 mm above the antenna, and 15 mm above the antenna. So you can see that 12 mm above the antenna, the concentration is more. Thereby, it is the gain is enhanced. So these are the simulated and measurement results of the S11 parameter. So S11 parameter is shown here. So this is a comparative study of a different height versus the gain of the antenna. Height versus the gain of the antenna is also shown here.
Excuse me, sir. Small doubt, sir.
Yeah.
Sir, whether we want to provide some space between the superstrate and the material, sir, normal antenna, is it required, sir? The space.
Yeah, the space is required. In this case, space is required. In some cases, the space is not required. You can see like this. Normally, what I have seen is in low frequency, the space is normally kept, but in high frequency, uh, it is okay. It seems. Whatever the work I have done, the space is important there. You
Thank
got
you.
it? So I have seen somewhere this space is not required. So for example, in some MIMO antennas and all, people use metamaterials as EBG structures and AMC and so on. There, they have not kept it even without space also. Okay. Yeah, this is the radiation pattern, E plane and H plane. Radiation pattern drawn for that, measured and drawn. I think these things you. So this is the gain uh, efficiency plots. Yeah, we have calculated the aperture efficiency as well. So aperture efficiency is calculated based upon the aperture size as well as the gain of the end. So there are different efficiency we can found. We can find the radiation efficiency that is available in the software itself. We can get radiation efficiency. If you want to measure this radiation efficiency practically, you have to use that Wheeler cap method and so on. So I have not done that Wheeler cap method and so on because Wheeler cap method, the experimental setup should be very much fine, and only you can be able to do it perfectly. So we have used the normal calculation. So these are the different comparison between the different literatures and so on. So this is published in International Journal of Communication and Propagation. So next one is the complementary metamaterial structure. So here the complementary version of the G shape is used. So this complementary G-shaped structure has given us a wide band effect. So I'll just tell you about the crisp of this. So here you can see it is working from 2 to 3 gigahertz, from 2 to 2.2 to 3.2. It is having the refractive index also of that order, and it was performing well in that range of area, and that is why we used this one. But the gain enhancement is not that much area. Here also 2 by 2 array is used, and here you can see we have, since it worked for a wide band, we have checked this one for a horn antenna. So we have checked it for a horn antenna. So the horn antenna was working from 2 gigahertz to 18 gigahertz, and in that it is working fine. So this is also tested for a particular frequency of 2.4 gigahertz as well. So here we are getting at a height of 11 mm from the antenna, we got a gain enhancement of 3.5 dB. So these are the different measurement setup used for the measurement. So these are the different radiation patterns for that. E plane and H plane. So the beam. So here, as you know, since the gain is reduced, gain is increased, something has to be reduced, right? So here the beam width is reduced. So beam is reduced by 5 degree in the E plane, and H plane has it is reduced by 20 degree. So some thing will be different. So also we have checked the beam steering of microstrip patch antenna with metamaterial superstrate. So beam steering in the sense this is not a kind of beam steering that use FPGAs, FPGAs and so on. So nowadays FPGA based beam steering is there. So this is a slight out of curiosity we have done some experiments. So this is the mechanical adjustments that we have done. So for example, so beam steering, as you know, it can be done on both sides. Like it can be done on elevation side as well as it can be done on the azimuthal side also. So azimuthal elevation both can be called as beam steering or beam forming anyway. So here we are rotating the superstrate that is kept above the antenna in different angles. Thereby what happens is the radiation pattern or the uh, radiation pattern changes towards that direction. So that one we have considered it to be the kind of beam steering that happens. Okay, so if you think like this is not the actual kind of beam steering, so just out of curiosity we have done this kind of experiments. So this is published in VAMS 2022. So next is another one interesting kind of thing, that is switchable active metamaterial superstrate for dual band gain enhancement. So this here we have used a switchable kind of thing. So here we are using an active element also. So which is pin diode is used here. Pin diode is used. So the ideology here is a novel active metamaterial superstate which is switchable to accomplish dual band gain enhancement is used here. So it works at 2.4 gigahertz as well as at 4.6 gigahertz. The gain of the antenna is enhanced by 3.5 dB at both the frequencies. So switching between the frequencies is enabled by using pin diode. So here as we are using a pin diode, it is active. We have given biasing also. So everything is given. Biasing and those kind of stuff. Everything has given. Okay. So this is the evolution of the structure. So this evolution of the structure is given like this. So how it is done? So we first started with the cross structure, then it is made in the shape of the S and inverted S. So when we then we made it on both the sides. So front, top and bottom, both the sides it is available. Then what we have done is we have introduced a gap in between. So this gap helped us to so why we have increased the size of the effective length is usually increased to reduce the size of the antenna. So effective length is increased. When we increase the effective length, the antenna worked at 2.4 gigahertz, or when we introduced the slit, what happened? It worked at 4.6 gigahertz. That is how this thing is done. So we have made a cut here and we joined it using the pin diode. So when the pin diode is on, again the cut is so this there will not be any gap, right? So when the pin diode is on, there will be off, there will be some gap. So that is the idea behind this. So here you can see the three-dimensional kind of thing here. A slit is introduced, they are shaped to control the resonance between 2.4 gigahertz and 4.6 gigahertz. So yeah, so this shows the transmission and the transmission magnitude as well as the phase characteristics. The entire dimension of this unit cell is about 14.3 mm. So in order to test this one, we have used the same antenna, patch antenna. Our patch antenna is actually a narrowband patch antenna that is working at 2.4 gigahertz. So I use the second resonance of that antenna. The second resonance is the harmonic resonance, that is at that should be at 4.4. But in our practical or our fabricated stuff, it was working at 4.6 gigahertz. So that was handy for me to check at both the both the directions. But as you know that the dominant mode creates the first resonance whose radiation pattern is directional, whereas the second resonance is not that direction. So this is the equivalent circuit of the pin diode that is used for characterizing in the software. We are using HFS software in which we are using this one. So this is on condition is this B, off condition we will have a capacitor also. So this equivalent circuit is taken from the data sheet of SMP 1320079F, which is having a biasing, which works at a biasing voltage of 0.8 volt. So these are the extracted parameters, one showing frequency versus permeability, frequency versus the real value of permeability shows 0 crossing at 4.6 GHz. The real and the imaginary value of refractive index has near 0 at 4.6.
Sir, excuse me, sir.
Yeah.
Sir, I'm little bit confused on what is the use of that non-zero and zero refractive index, sir. Why we using that, sir? Can you explain that, sir?
You are asking the difference between zero refractive index and non-zero refractive index. Is it right? Is it
Sir,
that?
why we are calculating here, sir? That's the doubt.
Yeah. So the thing is that our gain is enhanced, right? Gain is enhanced because of the superstate. So how this gain enhancement happens? That is how we are saying here. If the superstate is having zero refractive index, okay, what happens is zero refractive index material has the property that whatever electromagnetic waves comes towards that, it will confines towards the normal. Okay. So our structure, when it is in on condition, it is having zero refractive index, and off condition it is having zero refractive index at another region. Okay. So wherever zero refractive index is there, at that place the gain enhancement. That is what we are saying. Okay. So for example, this one shows the off condition. At off condition, we have zero refractive index at 2.4 gigahertz. On condition, we have zero refractive index at 4.6 gigahertz. That is how it operates. So this is the schematic of the proposed antenna, where the this one patch antenna together with the superstrate is kept. So the distance between the antenna and the superstrate is 6 mm. So first structure we have got it at 12 mm. So here at the 6 mm itself it is working fine. So here that is why we told that it is not working on the principle of fabric parrot, but it is working on the principle of near zero refractive index. So actually, if you see this figure here, we have in simulation we have tested using 4x4 structure, but in measurement we have done only for 2x2 because of the biasing constraints we had. We have just used the wire connected to the Schottky diode, and we have done the measurement, and that is why we have not done it for the entire thing. But presently at our lab, people work using the biasing circuit is also done together with the structure. So here a DC bias voltage is given at 1.5 volt is given, and thereby it is tested for all. So this is the measurement setup that is used. So this is about the S11 measurement, which is for the measured one as well as for the simulated one. Everything seems to be fine. So these are the normal things, the gain as well as different things, radiation pattern, radiation. So the radiation efficiency, it is drawn here. So this shows the radiation pattern. So radiation pattern, as I told you, this is the normal radiation pattern as at 2.4 gigahertz. And if you see here, it is the radiation pattern at 4.6 gigahertz. So the radiation pattern here is a little bit different because of the harmonic frequency at 4.6 gigahertz. It is different. So this is also the radiation pattern measured using an instrument called as RF Expert, which is used for measuring the radiation pattern, not by rotating and all. We can just keep it above the RF Expert itself. It will calculate the near field by which it can find out the far field results. So this shows the different kind of comparison. So this is also published in Progress in Electromagnetic Research. So next one is about reflective and transmissive near zero metamaterial superstate in gain. So here actually, yeah, kind of checking as we have done uh, for to see the effect of reflective as well as transmissive kind of unit cells and their role in gain enhancement. So in papers you can read that there are reflective metamaterial structures as well as transmissive metamaterial structures. So we have taken a normal S kind of structure whose property can be made reflective as well as transmissive. For example, how that is made is based upon slight movement between these values. For example, here you can see this S11 and S21 graph here. For example, we call it as S11 as reflection and S21 as the transmission, right? So when S11 is lower, we can say that transmission is higher, and when S11 is higher, we call it as transmission 0, right? So based on moving that, based upon changing the dimension of the unit cell, I can call it as reflective as well as transmissive. So here in this case, for example, if you see at 2.4 gigahertz, S21 is minimum, S11 is maximum. So I could say that it is not allowing anything to pass at 2.4 gigahertz. So I call it as reflective because it is reflecting everything. And if you see the next one, at 2.4 gigahertz, I made this S11 to be minimum and S21 to be maximum, and that is the place we call it as transmissive. And this is also simulated and find it out. So you can see the electric field orientation of this reflective thing. Port 1 we are making the excitation, port 2 we are observing the result. So here you can see when I am using the reflective unit cell, most of the thing is reflected back, but when I take the transmissive unit cell, most of the things are transmitted. So these are the two kind of unit cells available, reflective as well as transmissive units. Okay. So this both the things are taken and it is analyzed using you analyzed for different kinds of array, for single element, for 2 by 2, 3 by 3, 4 by 4, and a comparative study is also done for different values and different. So I am not going to explain much on this. You can just refer this paper. It is published in a conference IndyCon 2022. Now I am moving on to the next kind of work, that is called as interdigital capacitance coupled electric ring resonator. So you all may be aware of this interdigital capacitance. It is a very familiar capacitance that is used for filter design. In filter design, most of the people work with that structure because that is a good bandpass kind of filter structure that can be used everywhere. So I'll just show you how it is done. So here you can see this structure. The center portion we have included the interdigital capacitance kind of thing. So by increasing the capacitance value, we were able to reduce the size. So here you can see interdigital capacitance based design has reduced its size by 50% compared to the normal electric ring resonator. So normal electric ring resonator is also available. So normal electric ring resonator, what happens is it is just a space here. So when you when you include this interdigital capacitance, what happens is the size becomes very small. That means the total size of the unit. So thereby it is reduced by 50%. So the gain enhancement is also increased by 4.2 dB. So earlier it was 4 dB. So here gain is also increased by 4.2 dB higher. So the things and all is done the same, because here also we are making it as a 4 by 4 units structure, and we are keeping it above the units antenna. So when we analyze the electric field parameters, the interdigital capacitance has a more electric field density. So the all the other things and all is more or less the same. So here also we are finding out the electric equivalent circuit. So here you can see how I have formulated the inductor and capacitance value. So the normal conductor I am taking as inductance, and the gap which I am taking as capacitance. When I have multiple gaps, I'll combinedly take it as a single capacitance. So this shows the S11 and S21 of the equivalent circuit as well as the normal thing. So this is the formula that is used for finding out the interdigital capacitance. So this is how the equivalent circuit we are giving the value to be 2.64 picofarad. So these are various parametric analysis is done by changing the width, thickness, gap, etc. And we have formulated a formula for this one. So this is the design equation that is derived for this structure. So L1 equal to 32 and so on, where all the parameters are involved here. One second. Yeah, sorry about that. So this is the equation in which all the parameters are involved, and for which the values length can be calculated for different frequencies. So there is a constraint also. It cannot be used for all frequencies because some frequencies it won't work. Therefore, that is also given. The range of frequency in which it works is from 1.432 lambda to 3.896 lambda. So this is the proposed structure. So the dimension of the unit cell is very small, and it is kept above the antenna, and it is giving a gain enhancement of 4.2 dB. So all the works we have kept the size of the antenna as well as the superstrate to be the same. That is of dimension 104 mm by 104 mm. So here also the gain enhancement is obtained at about 12 mm from the end. So here also it is kept at about of 12 mm from the end. So this is the experiment setup used for gain and so on. So these are the simulated addresses for E plane as well as the H plane. So this is the radiation pattern for E, co and cross. Okay. So this is also published. So the last topic which I am going to take is low loss near zero metamaterial superstrate for gain enhancement. So in this low loss superstrate, we are introducing a different substrate for using for making this metamaterial. So this is using material. So I will show that. So this is the substrate that is used. On the right hand top, you can see the substrate. So that substrate is made in collaboration with the NIT Calicut mechanical department. So they used to make substrates. They used to make substrates of different dielectric constant. So here the dielectric constant obtained is 11.7, and the loss tangent is 0.0048. So that is actually smaller, very much smaller compared to that of FR4, because you all know that FR4 is having a dielectric constant of 0.02. So here it is 0.0048, so that is smaller than that. So that is used, yeah. The dielectric constant is also higher. So dielectric constant, when it become higher also, it will have a reflective effect that also enables gain enhancement. Suppose if you just keep a FR4 substrate above the antenna also, it will give a gain enhancement of about 0.8 dB or so on. So dielectric itself has some effect. So when you use a high dielectric constant substrate, that will be better. So normally we don't use high dielectric constant material for making antennas because of its less radiation efficiency. So since we are using as a superstrate, that will be fine. So here we have made a different analysis of study of microstrip using different superstrates. So here we have made some analysis of different dielectric constant, different loss tangent, and then we have seen the gain enhancement. We take the normal FR4 substrate, which is having 2.2, no, dielectric FR4 is having 4.4, right? So 4.4, you can obtain a gain enhancement of 1.01. But if its loss tangent is 0.2, you'll get 0.65 only. So throughout this, if you see, as the dielectric constant increases, the gain enhancement also increases. Similarly, when the loss tangent decreases, the gain enhancement increases. So we are incorporating these ideas together with the near zero dielectric, near zero refractive index concept. So higher dielectric constant, less loss tangent, and near zero refractive index. So when you incorporate all these three things together, what will you get is the same gain enhancement is obtained when you this. So this is the structure that we used for this substrate. So which is giving near zero refractive index, and yeah, this is the near zero refractive index that is obtained, and which is kept above the superstrate. Yeah, this is kept above the superstrate. So since they are giving it as a circular kind of thing, I have used that circular thing itself, and it is kept above the antenna, and it is giving a gain enhancement of about 4.6 dB. So a gain enhancement of about 4.6 dB is obtained. So these are the different kind of structures that is used for the gain enhancement. So these are the different structures used. So this is a radiation pattern that is made, radiation pattern measurement. This comparison. So this is also published in peer journal. So future scope of this research work, it can be used in wearable applications. So matching improvement can be done for high gain antennas, symmetrical metamaterials for gain enhancement for even we have tested only for linear polarized, go for circular polarized, improving the biasing techniques of active metamaterial superstrates, thereby giving how the biasing can be done and so on. So with this, I stop my presentation and I'll take some questions if you have. Thank you very much for your patient hearing. So it is nearing 9 o'clock. I think you'll all be ready for the
Thank you so
dinner.
much, sir. Great presentation, sir.
Yeah, thank you very much.
Good evening, sir. I have a small doubt. Am
Yeah.
I audible, sir?
Yes, audible.
Sir, I just wanted to check out, we are seeing that phases of this superstrates, whatever your design as metamaterials or periodic structures.
Okay.
So when we see that phase for S11 and S12, both are looking like 180 to 180.
180 to 180. Actually, the point of interest in which I am looking, I am looking at the phase change 180 to 180 uh, for only at 2.4 gigahertz for S21 only.
S21.
So yes, what you are speaking about the 180 to 180 is for the reflective as well as reflective
Yeah,
and transmissive. There I am
both,
not
both.
speaking. Yeah, there I am not speaking about this near zero and so on. Because
Actually,
yeah, tell me.
the thing is that I am trying to design such a metamaterial. But I'm not able to get both as 180. Only S12 I'm getting. I need both to be. Means I just wanted to act it as a reflectors.
Okay.
So I need both to be in S11 as well as S12 to be both in 180 phase shift, right, sir?
Mhm. So what is the kind of design you are using?
So I
What
just
kind?
simple loop only.
Okay.
Even that basic loop I'm getting only S12 as 180, and the other one it is close to 90 only I'm getting.
Okay.
What may be the reason?
I don't know why it is like that and all. Normally, we used to take some standard structures and we have to work out. I am very sorry that I can't.
Sir,
Uh,
can you please show me your reflective sections, the phases what you have shown in for one or two that S structure like
yeah. This one, right?
yeah.
So
So
in this structure, actually, I was not looking anything on the face. I was only looking on this S11 and S21 because there I was speaking about this reflection means there the S11 should be higher and the transmission means the S11 should be lower. That is the concept I have kept in my mind, and that transmission reflection phase I have kept, but I am unable to tell exactly how it is and all. But
when I
normally,
saw for the basic section also there it is like 180 to 180, but I'm whatever I do it is not able to reach 180 for me for S11. I just wanted that to be worked as an reflector.
okay. Normally, this 180 to 180 normally we will get for all the structures. Like that's a simple thing usually people used to get. The other kind of you can try with some.
Is there any technical concept that where we should change alterations or something like
Have you searched
based
about
on the current surface?
this electromagnetic band gap material and so on?
Yeah, okay.
Those transmission.
I just checked for a single loop, square loop alone. Still, it is not
Okay.
getting for me.
Okay, I'll check. You can just mail or something. I will just how. Okay.
Uh,
Sir, can I just contact you tomorrow such that I can show my design to you?
Yeah, you can mail me or message me in WhatsApp. That would be fine. Okay.
Sure, sir.
Yeah.
Thank you, sir.
Thank you.
sir, excuse me, sir. Excuse me, sir.
Yes.
Sir, what kind of approach should I consider to get gain enhancement along with polarization, sir? What kind of approach shall I go, sir?
1 second. Yeah, can you repeat your question?
So what kind of approach should I consider for both gain enhancement with polarization in reconfigurable antennas, sir, using superstate? Is there any specific technique, sir? Like with pin diode and superstrate, what kind of approach should I consider, sir, to get both the gain enhancement and polarization? Can you hear me, sir?
Is it polarization intensity device?
Not normal reconfigurable antennas, sir. You, if I use superstate like that, what kind of approach should I consider, sir, for both gain enhancement as well as to get the polarization?
What do you mean by get?
What, sir?
What do you mean by getting the polarization?
No, sir. Like circular polarization as well as gain enhancement. If I want to achieve both, what
Yeah,
should
yeah.
what type of?
Yeah, for that you have to go for some identical symmetric structures. So all the design which I have done is not symmetric.
Okay, sir.
Okay.
Okay, sir.
Yeah. Any other questions?
So how did you calculated the permittivity and permeability? Did you use any MATLAB code for the same or direct through the software you have used?
Actually, I had a net problem. Can you repeat the question? Hello?
So the question is how the permittivity and permeability is calculated. Have you used MATLAB code to calculate that, compute that?
Yeah. Yeah, I have used MATLAB code for computing that. I have used the modified Nicholson-Rossware method. We have the formulas for that, and using that, I have calculated. If required, I can send it to you all.
Yes, sir, please. That will be a great help if you could be
That
able to
code
share
as
that
well
code.
as. Yeah, sure. Yeah, sure.
Can we do that in CST, no, sir? You mentioned that it is available in CST, right, sir?
It is available in CST in post processing
Am I
that
audible,
we can
madam?
calculate.
Yes, sir. Yes.
Okay.
Dear participants, expert has shared his number in chat box. You can chat with him and clarify your doubts. Any other queries? Participants, do you have any other queries? Yes, we will share the recording once the program gets over. We will share the recordings. All the session recordings will be sharing. Expert has shared his mail ID also in group in the chat box. Thank you, sir. Thank you very much. Actually, this is a last minute request to Arun Shaji sir to take a session. He has taken it in an excellent way. Hope all participants enjoyed it and you got an interactive session. You got a great knowledge about metamaterial design, how the results have to be analyzed. Thank you, sir. Thank you for spending your valuable time. Thank you all participants for your patient participation and attending this workshop FDP. Thank you all.